is 12, 2, 15, and we're going over the 3-3 FIP quiz. This is angled launch projectiles. So for our first one, we're told that a football is kicked at, so it leaves the ground at 27.5 degrees above the horizon. If the football hits the ground 48 meters from where it was kicked, what was its initial velocity? So we're looking at a situation like this, where delta x is known to be 48.0 meters. We don't know, nor do we care, what delta y max is, because we know what delta y overall is. So if we do our x and y variables, list what we have there. Vix, of course, is equal to the cosine of theta times vi. Viy, the sine of theta, vi. And delta x we have as 48.0 meters. Delta y is 0, and that makes our math a lot easier. Acceleration on the y-axis, negative 9.81 meters per second squared. And delta t will again form our bridge. Okay, so delta t, we can, on the x-axis, because there's no acceleration, we can do our old trick of delta x over vix. And then on the y-axis, we can build an equation that will allow us to substitute in that value so that we tie the axes together. So we're going to use this equation to tie our axes together. And I wanted to make it really clear, because I know at least one person had mentioned that it wasn't totally clear. When you start off with those equations that are just coming out of one axis, everything represented in that equation has to be representative of that axis. So here, everything we're talking about has to be y-axis values. So that vi is viy, that acceleration is acceleration on the y. We'll start to substitute and connect them, but initially when we write equations for each axis, they have to just reflect that axis. So I don't know if that was unclear, but now it should be clear. Okay, so now we've got a way to substitute these in for the delta t's. And we're going to be rearranging for vi, which seems, well, doesn't seem impossible. To be done. I'm going to start off by putting in my expressions for viy. So vi times sine theta delta t plus 1/2 a on the y delta t squared. Then I can put in this expression. So delta y equals vi sine theta times the quantity delta x over, and of course vix is just vi cosine theta, so I put that in, plus 1/2 a on the y times delta x over vi cosine theta quantity squared. So at this point, I can start doing the serious work of rearrangement. I'm going to take it to the next page. Okay, so trig identities really help you here because you can get rid of that, you can get rid of the fraction here. So if the first thing we do is to distribute this across what's in the parentheses, we end up with vi sine theta delta x over vi cosine theta, and now it's plus 1/2. Well, actually, we can distribute across here too. So we end up with a on the y times delta x squared, because we're distributing the exponent too, over 2 vi squared cosine squared theta. So we now have two fractions to deal with, but we're going to be able to get rid of one of them using trig identities. So our vi's go away, which is good because that means we don't have to do a quadratic solve. We can get rid of the notion of quadratics. And sine divided by cosine gives us tangent. So we have tangent times, tangent theta, forget that theta, times delta x. So now we've gotten rid of one fraction, plus a on the y, delta x squared over 2 vi squared cosine squared theta. So this is a lot more manageable. We know that we have to start by, we're working towards isolating this. So since we're working towards isolating this, we want to first get this over to the other side of the equation, that expression, tangent theta delta x. And that's an addition-subtraction thing. Okay. There are a number of ways to approach this algebraically. What I find to be the simplest is to think of this as really being made up of two expressions. So I'm going to kind of mentally replace this with 2 cosine squared theta times vi squared theta. All I did was reorder how they appear in that numerator, or denominator rather, sorry. So I kind of think of that as two expressions, and I think of this as a single expression. So I'm going to replace this. Okay, so at this point, I know that I can multiply both sides by 2 cosine squared theta to isolate vi squared. Yeah, you can also multiply both sides by vi. Yeah, that's actually probably more direct, isn't it? Yeah, I like your way better, Skylar. I don't remember what I did on the key. So we've now got the vi, yeah, we've got the vi squared over here, and we've gotten rid of it there. So now we can divide both sides by this expression, if I can manage to pick it up. Which gives us that, and we're almost done. Because now all we have to do is take the square root of the whole mess on the one side to eliminate our exponent. Ma'am. It is, yeah, that goes away. Yeah, and so other good point, that's actually 0. So really that expression is just negative tan theta delta x. You can eliminate the delta y at any point because we know it's 0. So, okay, then it's plugging in. Okay, you show something that looks like this. It's of course a booger for calculator entry, so that's a common source of errors. Do it however you need to. But the final raw answer that you get, 23.97, and it goes on, meters per second. And so for a 2 sig fig final answer, we'd have 24.0 meters per second. Okay, questions on that one? Okay, so we've got somebody being shot out of a cannon, and we have an initial velocity and we have an angle, and we know that there's going to be a net 50 meters out. So what we're interested in is, at the point when delta x equals 50 meters, what's the y displacement? What's the delta y? So we need to tie the axes together. We've got our standards for x and y axis variables, vix, viy. Delta x, delta y is our question mark. And delta t, of course, is going to be our merger point. So we're going to use our old friend delta y equals viy delta t plus 1/2 a delta t squared. And that gives us a chance to connect the axes using time as our bridge. So I'm going to substitute in the values for initial velocity on the y. And I'm also going to substitute in the expression that we wrote for delta t. Whoops, okay, I had hit pause. I'm not sure where I hit pause. So we distributed across the fractions, got rid of our vi, and the next step will be doing that trig identity to get rid of one of the fractions. So we're down to this. At this point, there is not a whole lot more that we can do, and we're really actually ready to solve. So we're ready to plug stuff in. We're already solved for delta y, so our plug-in is going to look like this. Okay, our plug-in looks like this. I went ahead and put in values for the parts of the equation. So tangent of 45 is what? 1. So this is just 50 meters. This whole thing, this whole expression, I get a value of negative 39.24 meters. So our delta y at the point when we're 50 meters out is 10.76 meters. So we're 10 meters up in the air. Now here's the question. Where do we have to place a net? Because the question very specifically asks, where do we have to put a net to make sure you're caught? So let's look at what that number actually means, because getting the number in a lot of physics problems, and especially when you go on to engineering applications, getting the number is only half of the battle. Understanding what that number is telling you about the situation is the other part. So let's draw the picture again and look at what that means. So we know you're at 10.76 meters. Do we know if you're above, or do we know if you're before the max height or after the max height? We really don't. We could figure that out if we did a max height calculation. You know, the assumption kind of is that we're somewhere here, right? What would be some other ways to figure out if you're beyond max height? I mean, other than doing a maximum height calculation, do we have enough information to do a max height calculation? Why would we need to know if we're beyond max height? And I realize I didn't reflect this in the key. I did my own mental process, but I didn't reflect it. So what if, instead of being here where I'm asserting we are, and we're on the down trajectory, so if we're on the down trajectory, hey, life is good. We stick a net at 10 meters, and the trajectory continues, and we hit the net, and life is fine and happy, and nobody gets hurt. What if you're still on the up path? You're going to go flying right past the net. So if in fact, instead of being on the downward part of that trajectory, if in fact, instead of being on the down part of the trajectory, you're there, you can stick a net at 10 meters. It's not going to do you any good because you're going to blow right past it and keep rising. So how could we use this information to get a delta y max? This is actually really simple. What's the maximum height for delta y? Well, all we have to do is look at the y-axis alone. And if we look at the variables on the y-axis at max height, if we look at the delta y at max height, we still have VIY. We know what VFY is at that point, don't we? 0. We have that moment of 0y when you... How many of you have been on a trampoline? Okay, there's that moment at the top of flight where you stop for a second. Ah! And then you fall. So that's 0. We know acceleration on the y. And if we want delta y max, we can simply look at it on that axis. We don't actually have to marry the axes here because we're just looking at the motion on the y. So, whoops, VI sine theta. What expression do we have that ties those together neatly? The squared one, yes. VFY squared equals VI y squared plus 2a delta y. So that's, do you want me to do the algebra fast or slow? We know that this is 0. So 0 minus VIY, we have negative VIY squared over 2a gives us our delta y max. So go ahead and plug that in real quick. As I said, sometimes there's more to a problem than I realize when I write it, and I just realized with this one there is more to it than when I wrote it, or than I thought there was. So here's what we know. Here's the trajectory for this object. Here's max height. We'll say 32 meters. We don't know, because there's going to be a 10.76 somewhere here, and there's going to be a 10.76 somewhere here. Hey, sorry, I screwed up. That max height is not 35 because this is just VIY. So that's VI times sine of theta. Okay, so then to correct this, this is not 32, it's about 16. But we still know that there's a 10.76 on either side of that. How do we figure out if that's on the up or the down? How could you actually figure that out? Okay, so that's a good thought, and that's kind of what I want you to do, is think about sort of creatively how would you figure this out. So point raised, well, isn't it on the down because we used 50 meters? But we don't know at what point. Yeah, that would be one way to do it. So there'd be two ways to do it. One would be to find delta x at delta y max. One would be to find, okay, if you go all the way back down to cannon level, so if you complete the trajectory and you don't get caught, how far do you go total? But actually doing that would probably be better. And we're not going to do it. I just want you to be thinking about that. You know, like I said, there's more to a problem sometimes than I realize when I write it. There's a real limit to the number of problems you can write and not go insane. The more physics problems I write, the more I admire textbook authors and realize that a large portion of their work is writing problems. Oh my God, that buzzing is terrible. Okay, questions, comments, concerns on that? Okay, so all that we're gonna leave it aside, and let's do number 3 together. Okay, so this one was actually it was an easier problem because I gave you VI. So, you know, you start off doing the whole listing, and you have, okay, VIX is cosine theta VI, VIY is sine theta VI. What we want to know is delta y max. So if we just want to know delta y max and we already have VI, we can just look at this motion on the y-axis. So we've got VIY. What is VFY at that moment at top? 0. It's going to go to 0 for a second. So we have that. We have acceleration on the y, negative 9.81 meters per second squared. And we want delta y max. So we can actually do this just simply on one axis. Most common mistake here is the same one I made in the last problem, forgetting to use VIY and using the entire VI, because not all the VI is on the y-axis. So we can use VFY squared equals VIY squared plus 2a delta y, solving for delta y. Okay, so we've got that, and we know that's 0. So the negative of, now we're going to do our substitution, VI squared sine squared theta over 2a will give us our delta y max. So we have 23 squared sine of 15 squared times 2 divided by 2 times acceleration due to gravity, 9.81 meters per second squared. We get a raw answer of 1.8061. It goes on and on and on. And so with sig figs, we get 1.8 meters as delta y max. Applications for this, if you're somebody who likes to ride your bike off of ramps, sometimes I have students who do. You can actually figure out what angle of ramp and what velocity you need to jump an object. So Oh, what fun. 1.8 meters in the air on your bike is not totally insane. I've had students who say they've been that high on their bike in the air, jumping off of things. Better them than me. Questions, comments, concerns?
Hold on, let me finish.
Okay, I'm going to let you finish. Tomorrow I'll have a mixed FIP. What that will involve: horizontally launched projectiles, angled launch projectiles, and I'll toss in for good measure like one resolving, solving. I'll put in one multiple vector problem too, just so it'll give you a flavor for what the workout test is going to be like. Okay, so it's gonna be a rough quiz, is what I'm saying. But I want to give you that experience of all those kind of problems in one place, 2 periods, go, so that you're better prepared for the test. It's a FIP.
Are we gonna be able to have like a
It's a
second
FIP.
one of those? But I would do like that.
I don't.
Even if it's just like take home or something.
I could do a take-home one. Yeah, I could do a take-home. Okay, that's it for today.